So, have you ever actually wondered why our absolute smartest, top tier AI systems, systems with massive amounts of computing power, why do they still get stuck? Like they fail to find the absolute best solution to a complex problem all the time. Whether it's, say, a robotic arm getting inexplicably tangled up in an automated factory, or a fancy financial algorithm just completely missing a huge market trend, they get stuck. It's a pretty fascinating paradox, right? We build these incredibly sophisticated agents, set them loose in continuous environments, and yet they end up trapped on just mediocre solutions. Well, welcome to this explainer. Let's dive right into this, because today we are unraveling exactly why this happens, and more importantly, how a seriously mind-bending new approach is solving it.
Our focus today is on a groundbreaking new framework called QuantFPFlow. In simple terms, this framework uses a really clever, quantum-inspired mathematical trick to basically help AI see the bigger picture. Instead of just stumbling around blindly, QuantFPFlow gives the AI a master map, radically accelerating its ability to find the true, absolute best solution in a complex environment.
Section 1. The Local Optimum Trap. Uncovering AI Blind Spots. To really grasp why this is such a huge game changer, we first got to look at the fundamental flaw in classical continuous reinforcement learning. Imagine an AI agent trying to find the very highest point in a terrain like this. Classical algorithms are, well, they're inherently greedy. They start climbing literally the very first hill they see. And once they reach the top of that first hill, which is the local optimum, they look around, see that every single step from there leads downwards, and they just stop. They get totally trapped by the barrier in the middle, completely missing the true peak, the global optimum, that's just waiting for them on the other side. Think of it kind of like an AI hiker lost in thick fog. A local optimum basically means the hiker has climbed to the top of a small mound. And because the immediate steps in every single direction go down, the hiker mistakenly thinks, hey, I've conquered the mountain. They plant their flag on a molehill, and they stop. They have absolutely no idea that just a mile away, hidden by all that fog, is Mount Everest. That is the tragedy of greedy AI algorithms. So, the big question is, how do we clear the fog? Section 2. The Fokker-Planck Blueprint, Mapping the Board. This brings us to the theoretical solution for AI's blindness. We can contrast our standard classical methods against this completely new approach. Classical methods like soft actor critic, or SAC for short, they greedily hunt for immediate rewards. Because of this, they're highly prone to what we call mode collapse. That's basically getting permanently stuck on that first hill we just talked about. The Fokker-Planck method, on the other hand, evaluates probability distributions across the entire space. It acts almost like a master blueprint of the whole landscape, mapping out the mathematically optimal stochastic policy rather than just chasing the nearest carrot. As you'll see here, this approach actually maps out all possible states over time. It propagates density from a totally uniform, flat starting point and eventually forms a stationary bimodal distribution. In plain terms, that means it successfully locates and maps both the local trap and the true global optimum. It literally sees the whole board. But, there's always a catch. While the Fokker-Planck equation is absolutely brilliant in theory, actually reading this blueprint on a classical computer requires what's called a partition function. And to calculate this classically, you have to use Monte Carlo sampling, which scales at big O of 1 over epsilon squared. What does that mean in plain English? Well, it takes way too much computing power to be practical for complex, high-dimensional AI problems. So we have this perfect map, but it's just too heavy for a classical computer to carry.
Section 3. A quantum speedup. Achieving a quadratic advantage.
So how exactly do we fix that perfect yet impossibly heavy map? Well, we enter the realm of quantum mechanics. This is the real hero of our story, quantum amplitude estimation, or QAE. By integrating QAE, the QuantFPFlow framework achieves a massive, provable 1,000 times speed advantage. No joke. It uses a Grover amplified quantum estimator to shift the mathematical bottleneck from 1 over epsilon squared all the way down to simply 1 over epsilon. That is a provable quadratic speedup. And you can actually see this huge gap we're talking about right here. This is the quantum advantage gap. It's the visual, hard data proof of how much computation time is saved by shifting from classical Monte Carlo sampling to this quantum estimation method. It's not just some small tweak we're talking about. It's a fundamental mathematical leap. Section 4. Quantum exploration, the bonus equation. So how does this speedup actually change the AI's behavior? Well, it all comes down to this specific equation. Now, don't let the math intimidate you. The intuition behind it is actually beautiful. The augmented reward, which is what the AI is actually chasing, is just the normal environment reward, plus a theoretical bonus derived directly from that Fokker-Planck distribution. Basically, this equation actively incentivizes the AI to visit rare, unexplored areas of the map that are mathematically highly likely to be important. It literally pays the AI to ignore the easy wins and go out and explore the barrier between the hills. And honestly, the results of that bonus are stunning. On one side, you get the tragic mode collapse of the classical SAC algorithm. Despite having built-in entropy regularizers, SA's curiosity just collapses down to a mere 1.5 nats. Nats are the unit used to measure this entropy, by the way, and it gets totally stuck on one peak. But then, look at QuantFPFlow. Because of its structural Fokker-Planck constraints, it actively maintains its policy entropy at a highly curious 6.5 nats throughout the entire training process. It absolutely never stops exploring the big picture.
Section 5. Crushing the competition. QuantFPFlow results.
Now, with sustained curiosity and a literal blueprint of the landscape, you'd probably expect some superior results. And we have the hard data to back it up. QuantFPFlow achieved a definitive victory, with a mean reward of 1295.7, cleanly beating SoftDoctor Critic. But the real headline here? The global optimum discovery rate. QuantFPFlow found the true peak 33.9% of the time, compared to SAC's 30.7%. That is a 10.4% relative improvement in finding the absolute best solution. Meanwhile, another classical algorithm, DDPG, suffered total mode collapse and only scored a 628. And the best part is, this isn't just for simple landscapes. As AI problems get absolutely massive with hundreds of dimensions, QuantFPFlow scales beautifully. Its computation time scales at big O of d to the power of 0.35. Compare that to the classical Fokker-Planck solver, which scales at d to the power of 0.76. Basically, as the complexity and dimensionality increase, the classical method skyrockets in cost, while this quantum-inspired method stays incredibly efficient. So let's summarize what you should really take away from all this. QuantFPFlow is an absolute breakthrough because it actively eliminates those frustrating local optimum traps. It gives us a provable quadratic speedup in mapping the environment. It strictly prevents the AI from losing its curiosity and collapsing its entropy. And perhaps most amazingly, this was all validated using a quantum-inspired classical simulation, meaning it works on classical computers right now, today, but its algorithmic structure is fundamentally built to be plugged directly into the quantum hardware of tomorrow. Which leaves us with a truly exciting prospect to think about. If a classical simulation of this quantum math can already outsmart the best classical algorithms today, what exactly is going to happen when we unleash QuantFPFlow on true, fault-tolerant quantum hardware tomorrow? The AI landscape is about to change forever. Thank you so much for joining me for this explainer, and I really hope it sparked your curiosity as much as it did mine.